Okay, this is section 10.4, the Webwork, problem 6, where you're asked to find the area of the green region that's shaded. So the two curves, I've written down the equations for this version of the problem. The green curve, which is my cardioid, is given by r equals 10 plus 10 cosine theta, and the circle is, in red, is r equals 15. So I'm going to have to find the points of intersection here, which are this point and this point. So what I really need is to know what angle that is and what angle this is. Okay? And so once I know those two angles, I am going to obtain this part of the region in orange by integrating the equation of the circle, 1/2 15 squared, from the first angle to the second angle, because the boundary of that part of that region is on the circle. Right, so let's find those points of intersection. I'm going to have change colors here to blue, say. So 10 plus 10 cosine theta is 15. 10 cosine theta equals 5. Cosine theta then is 5/10, or a half. And then I know that that means theta is pi/3. So this angle is theta equals pi/3. The other angle is theta equals minus pi/3, because the cosine of that is also a half. So let's write that. So theta equals minus pi/3 would be this angle. So my orange region is going to be the integral from minus pi/3 to plus pi/3, 1/2, oops, okay, 1/2 15 squared d theta. Okay. Now, to get the other parts of that shaded region, the boundary of those parts is on the cardioid, right? And so I'm going to have to sweep out the cardioid from the pi/3 to this angle, which I actually, if my first limit of integration is going to be pi/3, I should call the second angle something bigger than pi/3. So I should go to 5 pi/3. So I can, to get the blue region, that's going to be the integral from pi/3 to 5 pi/3, 1/2 10 plus 10 cosine theta squared d theta. So I would compute those two integrals and then add them to get the area that I want. Okay, this is section 10.4, problem 5 on the Webwork. So for this version of the problem, we're given this sort of rose curve with 4 petals, whose equation is r equals 2 plus sine 4 theta. And then the circle in red is r equals 2, and we want to find the area of the shaded region. So again, we're going to have to find the points of intersection, which are right here. But I can tell from the picture that one of them is going to correspond to theta equals 0. So I just have to find this angle as well. So I do that by setting the two equations equal to each other. So sine of 4 theta has to be 0. So what angles have sine equal to 0? Well, multiples of pi, right? So 0, pi, 2 pi, etc. Which means theta would be 0, pi over 4, and 2 pi over 4, but I think I just need those two. So theta equals 0 is one of them. I kind of knew that from the picture, and now I know that the other one is pi over 4. So here, theta equals pi over 4. All right. So, so how do I get the area that's shaded? Well, if I do the integral from 0 to pi over 4, 1/2 2 plus sine of 4 theta squared d theta, then what am I going to get? Well, I'm going to get the area swept out by the green curve between the angles 0 and pi over 4. So that would be this area in blue. Okay. All right. So that's not what I want. I want to subtract from that. So I'm going to subtract the integral from 0 to pi over 4, 1/2 2 squared, because that's going to give me the area between those two rays again, but only up to that circle. So it's going to give me that orange, and if I subtract that orange from the blue, that's what I want. Okay, so this is problem 4 in the Webwork for section 10.4. Again, we're trying to compute the area of the shaded region. And in this case, that region is bounded by the cardioid, which is the green curve, whose equation is given by r equals 8 plus 8 sine theta. And the circle in red, whose equation is r equals 24 sine theta. So as usual, I have to find the points of intersection, which are right here. Okay. And so I want to find that angle and that angle. Okay. And I'm going to do that by setting those two equations equal to each other. So set that equal to 24 sine theta. Subtract 8 sine theta from both sides, I would get 8 equals 16 sine theta. And then divide by 16, I get 1/2 equals sine theta. So theta is pi over 6. And then there's another angle in the second quadrant, which is 5 pi over 6. Okay, so this is theta equals pi over 6, and theta equals 5 pi over 6. All right, so if I integrate 1/2 24 sine theta squared from pi over 6 to 5 pi over 6, then what do I get? I get the area of the region between those two black rays that goes out to the red curve, the circle r equals 24 sine theta. So I get this region that I've shaded in blue. Okay, so I'm going to need to subtract from that the integral from pi over 6 to 5 pi over 6, 1/2. So I want to subtract this region now that I'm drawing in orange, and that's the region bounded by the cardioid, so the green curve between those two rays. So it's going to be 1/2 8 plus 8 sine theta squared d theta. And that's going to be it. Okay, this is problem 3 in section 10.4, and we're supposed to find the area of the shaded region once again. And here we have a what's called a limison. The equation is r equals 10 minus 20 sine theta, and it's got this inner loop that we need to find the area inside of. So what I need to do is figure out the range of angles that generates just that part of the curve, so I know what my limits of integration should be. So, I mean, just so you can see what's going on here, if I were to graph the equation as a Cartesian equation, where I put r on my vertical axis and theta on my horizontal axis, well, this just looks like a sine curve. When theta is 0, r is 10, and when theta is pi over 2, theta is 10 minus 20, so minus 10. And when theta is pi, r is 10 again, so it looks something like this. And you can see that so I start out when theta is 0, r is 10, right? So I'm there, which corresponds to this point. So this would be 10 units away from the origin, so at x equals 10. And then as I go through, let me pick a different color here, black. As I go through these angles right here, r decreases, so that's when this curve curves in towards the origin. When r is 0, I'm at the origin. So, and this is where my inner loop is going to start. It's when I traverse through these negative angles right here in purple that I go through that inner loop. When I get back to r equals 0, that's when I'm at the origin again. That's when the loop finishes. And then switch back to black. These angles right here would correspond to this part of the curve. Okay. So, so what I've got to do is integrate from this theta to this theta to get that loop. I mean, that's the only hard part, is to figure out what the range of thetas are, because the integral is going to be 1/2 10 minus 20 sine theta squared d theta, and I've got to figure out those angles. So I know that I hit those angles when r is 0. So that means sine theta has to be 1/2, and theta then would be pi over 6 and 5 pi over 6. So those are the angles that I need to, and that's the integral that I want.